Hello? Hello, could you hear me?
I can hear whoever was.
Okay,
was
okay.
You,
Okay,
yeah,
okay.
Great. Go ahead.
Good. Okay. Actually, I called directly from my phone instead of using a headset. Um, so I think, oh, I think today I will talk mainly about how to identify significant genes. But before that, I think we need to do some recap on the method. So here is the character with direction method. So you basically have control and experiment, and
Chaonan, if can I suggest something? Would you mind starting from explaining what you're doing and so on, because some people may not have seen your first presentation. If you don't mind, you can have whole hour if it takes you to present. But if you wouldn't mind starting from beginning, that I think would be better.
Okay, that sounds great.
All right, thanks.
Okay. So my presentation is about analysis of links L1000 level 3 normalized gene expression data sets. So we all know that the broad divides their data set into different levels. So the level 3 is normalized gene expression data sets with replicates, and level 4 is Z-score signatures of those replicates. So I start from level 3 to derive our own signatures using a new method. So our method is based on, it consists of two parts. The first part is to identify significant experiments, to identify the experiment which are significantly different from controls. And the second part is to identify significant genes, identify the genes that most differentially expressed compared to control. So in the first part, in identifying significant experiments, we only use the 1000 landmark genes. That's what they actually measured, and these results from using only the landmark genes are good for experiment level analysis, such as clustering analysis, just any analysis that doesn't involve individual genes. The second part is to use the full gene set, the 22,000 genes, landmark genes plus the inferred genes, to identify those significant differentially expressed genes. These are good for the gene level analysis. For example, either you want to do some enrichment analysis, or you want to use the differentially expressed gene list to query some existing gene list database to find similar signatures. So this is the experiment setup for most of the experiments in Link L1000. In this illustrations, the control, this purple dot means control replicate, and this blue dot means experiment replicate. So here's the concept of bench. So a bench of experiments, a group of experiments that share the same plate. Here's the arrangement of how they will do the replicates of one experiment. Basically, they put the replicate of one experiment into the same well of different plates, and each plate has its own controls. So this will be replicate 1 of this experiment, replicate 2 of this, and replicate 3 of experiment. this setup will have consequence on the analysis. So some statistics about 18 control replicates per plate, and there are usually 2 or 4 plates per bench. So usually an experiment has 2 to 4 replicates, and there are about 360 experiments per bench. So this is the first part, is to identify the experiment that are significantly different from control. We use this characteristic direction method, which is published this year in BMC Bioinformatics. So here's a simple illustration with an gene expression data that only mirror 2 genes. So the purple is control and the blue is experiment. So this characteristic direction method, abbreviated as CD method, basically first find using the linear discriminant analysis to find the segregation plane that best distinguish experiment from control, and then find a direction that pointing from control to experiment that is perpendicular to the segregation plane, and use this direction to characterize how the experiment is different from control. So all the information is encoded of the differential expression is encoded in a single direction. Mathematically, it will be a unit vector of 2 components. Each component match to each gene. So these 2 red arrows is basically the projection of this direction on the 2 axes, and corresponding the 2 components in the vector. So you can see, like in terms of magnitude or the norm of this projection, the gene 1 is large than gene 2. So which means gene 1 contributes more to this direction, the difference between experiment and control, than gene 2. In other words, gene 1 is more differentially expressed than gene 2. And if you examine the direction of these projections, gene 1 is positive and gene 2 is negative, which means gene 1 is upregulated in experiments and gene 2 is negatively regulated in experiment. So the signs of the components of this vector indicates whether genes upregulated or downregulated, and the squared value or its magnitude of the components indicates how much a gene is differentially expressed. So these are the CD method applied to other experiments, similar idea, and each experiment will finally be represented by a single direction. Then, if you want to compare the similarity or dissimilarity between experiments, we can simply compare if these 2 direction aligns together. If they align together, they are similar experiments. They have similar differential expression signatures, and if they diverge, they are not similar. And mathematically, this could be computed using this cosine distance, which is basically a measure of the angle between the 2 directions. So a smaller angle or a smaller cosine distance means similar experiment, and a large angle and a large cosine distance means dissimilar experiments. So if you do some preliminary analysis on any normalized level 3 data sets, you can observe this what we call plate effect. So this is basically a PCA plot of the 4 replicates of this taurine 1 perturbation experiment. And these dots, these 4 groups of dots are the controls that in the same plate with each experimental replicate. Remember, like the broad place the replicates of the same experiment in different plates, and each plate has its own controls. So you can say, like, the controls of different plates, although they are biologically exactly the same, there are systematic difference between them which does not reflect biology. So you cannot use all the control use all the experiment replicates and compare all the control replicates to compute the characteristic direction. So instead, we end up compute one direction for each replicate on each plate using all the plates, all the controls in the plate and the single experiment element in that plate. So for each experiment, we will have what we call CD replicates. So if it has 4 replicates, we will have 4 CD replicates. We simply average the CD replicates to get our final direction that represents the experiment differential expression signature. So here's an example of CD replicates of one experiment. This experiment has only 3 replicates. So if you compare the cosine distance of each pair of these 3 CD replicates, you can get 3 different distances between each 2 of these CD replicates. Then the average of these 3 distances is what we call the average cosine distance, which is basically a measurement of the overall alignment of the 3 replicate directions of the same experiment. So we expect if the experiment is not different from control. It's not very different from control. These 3 directions will be totally random. The angle between each 2 of them will be large, so the average cosine distance will be large. And if the experiment is significantly different from control, this CD direction replicates should be more or less pointed to the same direction. Then the average cosine distance should be small. So basically, we can use this average cosine distance as an estimation of the experiment strength, which means how much an experiment is significantly different from the control. Actually, we did some benchmark of this average cosine distance in comparison with this TOSS, which is the quantity that the broad used to represent the strength of an experiment. It's basically the top average Z-score of an experiment. The assumption in this benchmark is that if all the other conditions are the same, the experiment of a higher dose should elicit a stronger response. So we basically correlate the dose rank and the experiment strength rank for about 800 sets of experiments, and the experiments in one set are only different by dose. So we expect that if the experiment with higher dose should be stronger. So this is basically the correlation. You can see like the average constant distance is more correlated to those than these two assays. So by simply using the average constant distance, we can rank all the experiments from the most significant to less significant. But we definitely need a cutoff to tell us at which point we will define those significantly experiments that is significantly different from control. And after that point, the experiment will be not significant. So we use the null distribution to compute the cutoff. These arrows represent the CD replicates in a bench, the CD replicates of all the experiments in a bench. Recall that a bench is basically just a group of experiments that share the same plates. So this will be the CD replicate of experiment 1 mirrored on plate 1. This is CD replicate of experiment 1 mirrored on plate 2, and this is experiment CD replicate of experiment 1 mirrored on plate 3, and similar up to experiment 360. So this will be a pool of CD replicates. I just randomly draw 3 replicates from this pool of experiments. For example, I may draw the CD replicate of experiment 1 mirrored on plate 1, and the CD replicate of experiment 9 mirrored on plate 2, and a CD replicate of experiment 181 mirrored on plate 2, and treat this as the pseudo CD replicates of a pseudo experiment, and compute the average constant distance of this pseudo experiment, and use this as null average constant distance. I just repeat this random sampling process to 10,000 times, and we have 10,000 null average constant distances. This make up the null distribution of the average constant distance. So this is basically the histogram. We will pick the upper 5% here at the point of 0.9 and the cutoff. So all the experiments that has average constant distance less than 0.9 will be those significant experiments, and the experiment that has average constant distance larger than this value, they will be those insignificant experiments. So we did some benchmark in comparing the results of constant distance and the moderated Z-score signatures provided by Broad. So here we pick all the significant perturbations from this perturbation group. It's a subset of the links data. This group of experiments mirrors the gene expression response after the ligand perturbations. The ligand include the 4 different classes: the growth factors, the cytokines, and the interferon, and also some other perturbations that not belong to these 3 classes. You can see using our characteristic direction approach and using the constant distance. This is the MDS plot. We can differentiate between the different classes of ligands. But if you use Z-score and using the Euclidean distance as a metric, they cannot distinguish very clearly from each other. And actually, our method could reveal more subtle difference So here is the same plot, but we now color them by time points. So you can see for this growth factor ligand perturbations, experiments of 24 hours seems to form one cluster, and experiments of 1 hour seems to form one cluster here, and the 3 hour, 6 hour seems to more or less mixed. But if you use disco signatures, they just look random. So then we enter into the second part. Here our task is to identify the significant differentially expressed gene. Still the characteristic direction approach, but now instead of using the 1000 landmark genes, we use the 22,000 genes. This is the CD replicates of the full gene set of one single experiment. These are equivalent to the previous arrows, but here I use column of squares to place emphasis on genes. So just a different representation of the same concept. So here each column will represent one CD replicate of the full gene set, and the 7 squares, each square represents a gene, and the shade of the color represents how much the magnitude of each component, or how much the component is differentially expressed in one replicate. So this is 3 CD replicates of one experiment of the 22,000 genes. Still, we average them and then sort the genes by the squared component value. So the genes that have the largest component value are placed at the top, and genes with the smallest component value are placed at the bottom. So in this way, we already sorted the genes by how much they are differentially expressed. But we need a cutoff to tell us where we, from where we can say the genes up to which place we can say these genes are significantly differentially expressed. If you read the original characteristic action paper, it provided a new Gaussian distribution to estimate this cutoff. I tried to apply this method to the link cell 1000 data, but it did not work very well. So I turned to this rank product approach. This is basically a method published in 2004. I believe it's one of the most popular methods to find differentially expressed genes. Still, it starts from CD replicates as in the previous slide. To apply the rank product method, you first sort the genes in each replicate by their component value, and then each gene will have a rank in this replicate. And you do the same thing for the other 2 replicates. You basically sort this replicate, the genes in this replicate, by their component value, squared component value from large to small, and sort of genes in this replicate by their square from large to small. And then each gene will have 3 ranks in these 3 replicates. And the rank product is simply a product of all the 3 ranks for this gene in the 3 replicates. Then you compute the rank product of each gene, and you get a rank product vector. So in this vector, the component will be the rank product of that gene, and the smaller the rank product, the more likely the genes differentially expressed. So you sort the genes by rank product, you got the most differentially expressed genes at the top and the least differentially expressed genes at the bottom. You sort them from small to large. So this is the rank product approach. To find the cutoff, we still use the similar idea of rule distribution. We use all the city replicates of full gene sets of experiment in a bench. We got a pool of city replicates of the full gene set. We randomly draw 3 of them as pseudo experiments. We repeated the process in the previous slide using the rank product approach, and got a rank product vector as here. And then we random draw another 3 city replicates and compute a rank product vector here. And we repeated this process up to 10,000 times. And then here we got a 22,000 by 10,000 matrix. Since our aim is to find a cutoff for the rank product, I basically vectorize this matrix to a very long vector, and this will be the rule distribution of the rank product. I pick the top 1% at the value of 715 as the cutoff in this example. This is the histogram of this large vector. So then for an experiment, for a sorted rank product vector of an experiment, all the genes that has a rank product smaller than 715.4 will be the genes that are significantly differentially expressed, and all the genes that has a rank product larger than this 715.4 are insignificant genes. So this is how we estimate the cutoff. But since now we basically have 2 approaches to rank the genes using the rank products and using the averaged characteristic direction. If we apply the same cutoff, basically the same cutoff means if we find there are 300 genes, 300 genes are significantly differentially expressed using the RP method, we will pick the top 300 genes in this using CD method as the differentially expressed genes. So that's how the same cutoff means. Then here comes the question: will the 2 sets of 300 genes the same genes using 2 different methods? The answer is no. This is actually rooted in the difference of the nature of the difference of the mechanism of these 2 methods, but can be easily explained using 2 examples. So let's first consider the case 1. This will be the compound value of one single gene in 3 different replicates. So this gene has a very large component value in replicate 1, but a very small component value in other 2 replicates. So I think we will all agree with there. It is not like it's very unlikely that this gene is significantly different expressed genes because their component value are not consistent. But this gene will be ranked at the top in CD method because it has very large component value. So if you average them, even if you have two small values, you will still have the average result is still a fair large value. So it will be ranked at the top in CD method. But it will be ranked at the bottom in RP because of these two small component values, the gene will have very large rank in two of the three replicates and a small rank in the first replicate. So if you multiply them, you get the product will still be large, so it will be ranked at the bottom in RP. Let's consider another case, case 2. So here it's also a single gene. The three components, the three component values of single gene in three different replicates. So fairly large value in the first two replicates, and also a fairly large negative value in the third replicate. If you're using the CD method, you basically average of the three values, which result in a very small positive value. So it will be ranked at bottom in CD method. But since all the three component values are fairly large, their product will be small and they will be ranked at the top in RP. And this gene, I think we will all agree that it's also unlikely to be the differentially expressed genes because the component values are not consistent across replicates. So case 1, so these two cases basically illustrates how the two methods may rank the same gene in different places. And so what I do is basically take the intersection. So I only pick the genes that are ranked at the top by both methods. I think this is the safest way to get the differentially expressed gene list. But there's still this case 3. This is also single gene, 3 component values in 3 different replicates. It has 2 fairly large positive component value in 2 replicates and relatively small negative values in the third replicate. The average will be still large, so it will be ranked at the top in CD method. And since 2 of its components are large, so it will also rank at the top in RP method. But I think we will all agree that this gene is also unlikely to be a differentially expressed gene because the component values are not consistent. Their signs are not exactly the same. So we have to filter out this gene, the genes whose signs are not consistent across replicates. So here is our final differentially expressed gene list. So in summary, we use the RP to construct a node distribution to give us a rough estimate of where to draw the cutoff. Then we pick the intersection and then filter out the genes whose signs are not consistent across replicates and then got our final and differentially expressed gene list. So this is some results. These are the 346 experiments in one bench that have more than one replicate. So the y-axis are number of significant genes, and the x-axis is the experimental strength, which is computed using only the landmark genes, and it's the average constant distance. We call that a small average constant distance means a strong experiment, you can see they actually correlate very well. It's negative 0.96. So which means like we say if an experiment is strong, it has more differential expressed genes, and if an experiment is weak, it has less number of significant genes. I think this is a better approach than the broad Z-score cutoff, which if you query their API, their differentially expressed genes will be basically the top 100 upregulated genes by Z-score and the top down 100 genes by Z-score across all the experiments with irrespective of their experimental strength. I think this strict 100 gene cutoff will exclude many significant genes for those very strong experiments, and also include many false positive genes in those experiments which are not actually too much different from control. So this will reduce your power if you do enrichment analysis or query or gene lists to another database. So I think our approach may be better. We are currently in the process of processing all the level 3 data that are currently available using our queries direction approach. So we aim to provide the results after we process them in a JSON format. So the SIG ID will be the unique identifier of an experiment, and all this will be the descriptive information of the experiment, and we will then give the average consensus of the experiment, which indicates the strength of the experiment. Also the CD landmark, the calculated direction of using only the landmark genes, and the CD4, the calculated direction using the full gene set, and SIG gene index, the index of the genes that are significantly differentially expressed, and also the up genes and down genes. We basically pick the upright components in this index. Yeah, here's a reference. Yeah, I think this is basically all I want to present. Any questions?
Hello, this is Kai from University of Washington.
Okay.
Hi, I have a question. So, have you looked at the effect of interpolation? So, for example, if gene Y is interpolated from gene X in the L1000 data, if gene X is differentially expressed in your rank product method, is gene Y also more likely to be differentially expressed? So,
I haven't investigated that. I think I have to first know what their formula is before I can do this. Right? Yeah.
Yes.
Yes. I don't know.
We are very concerned about the effects of interpolation from our gene networks perspective, but I was thinking that this might also have quite an impact on inferring differentially expressed genes as well.
I think what you say would probably the case, because their basic assumption is that the genes are correlated. So if X, Y are highly correlated in algorithm, in their algorithm, then if X is differentially expressed, then Y is certainly very likely to be differentially expressed as well, since they are correlated, right?
Right. And because all of the replicates would be interpolated. So yeah. So yes, just a suggestion to look at.
Mm-hmm.
Thank you.
That's a good idea. Mm-hmm. Thank you.
Thank you.
Hi, my name is Yan. I'm from Dr. Bar Joseph's lab from Carnegie Mellon, and I have two
Uh-huh.
general. Hi, I have two general questions about the level 4 data. So the first one is that I noticed that for same cell type and the same perturbation type and the same incubation time, there are existing several different signature numbers, and I'm wondering why that's the case. Are they just basically different batches of experiments? And yeah, that's
Yeah,
my first.
they just different bench. If their cell line perturbation, those time point are the same, they should be the same experiment. Just different bench.
But
Replicates.
But I thought the signatures should aggregate different batches of experiments, or
Uh, I think uh, I think so. I think so.
yeah.
I think so. If they are, if you compare them, you find them consistent, you definitely should aggregate them as one. But it's also interesting to just average them by themselves and then see if they are
Oh,
really
I see.
match each other.
Okay. Okay. So my second question, yeah. So my second question is, can we download like a certain subset of level 4 data, for instance, all the data for a single cell?
I think you can't. You cannot.
Okay.
They provide their data in a big matrix. So, but yeah.
Yeah.
But you
And
can
also,
use their. They have scripts. You can, after you download the whole data set, you can use their script to select a subset of data.
okay. Okay. And also, so my last question is, so basically this slide on the screen right now, what
Yeah.
is that JSON signature output? Like, can we get that kind of output right now, or that's like a future feature?
I'm still running the process, and
Okay.
after I get the results, I definitely would man a single way to share them to the community. That's definitely our aim.
Yeah. And what is the target? Is the known target, or it's the target?
Oh yeah. If the target of the drug is known, it will be included.
Yeah.
If the target
So you
is
know
not
that from
known.
published. Yeah. So do you know that from published results, or you sort of predict that?
I think if it's included in broad annotation, I will include. I do not try to predict. It's just metadata.
Oh, so is that part of the level 4?
I mean, some experiment, I think they have.
Some experiment has this field. Okay.
Yeah, I think the Miami group probably do many of such works. Like they catalog the small molecules and their structures, targets. Yeah, I can potentially just pull their information and add the target to the results. Or you can just query an experiment and to find the target of the perturbation.
Yeah, okay, yeah, thank you.
You're welcome.
So Chana,
Oh,
I have a question.
Yeah. I saw your question in the text.
Yeah. So what are the controls that you're using?
Actually, I put I think in their metadata, they have a per type field, which indicates the perturbation type of all the experiments. And there are several different values, but I think there are maybe 4 different names for control. There are in some of the experiments, the label is BMSO. For some experiments, the value is control vehicle, and in other experiments, it's control something. But you can easily identify which replicates are controlled by using this prototype field.
Thanks. Any other questions? Okay, well, thank you very much for the presentation.
Thank you.
And I will again post the video of the presentation as I've done before. And it looks like next week we will have to cancel this webinar because we will be at a meeting, a whole bunch of us. Please, if you have any questions, you can email them to me or directly to the speaker so that we can keep the discussion going. Thank you.
Thank you.
Bye-bye.